My name is Alberto Barroso. I'm head of decision science in Tetra Pak, having worked in 16 years on data science. And today I will share with you the most important problem to be solved in any kind of decision science, data science teams, which is the portfolio optimization. In other words, what is the optimal sequence of your projects to maximize the value? So I will share some insights based on experience, and I will share also a formulation that maybe is interesting for you to know. Let's start. So the agenda today is the following. We will start talking about the decision science portfolio problem. And this is about the prioritization of your projects. And we are going to use the analogy of the vaccine development. It's a very similar problem to solve. The second element we will talk about is the formulation of the time to value function. I will explain you what are the key parameters of this function. And the last one, but not least, we are going to talk about risk management and how to optimize decision making. And I will explain you an example with our own portfolio. Let's start. Let's start from the beginning. What is our decision science portfolio problem? Well, it's quite simple. The question is about what is the right sequence of projects and what is the right investment in time and cost. So you will think about this problem about maximizing time to value. And the situation or the context today is that typically this is done based on experience, based on context, based on politics. So it's very much emotionally driven rather than data driven. So we have an opportunity. We have the opportunity of using a structured approach to define a set of toll gates and define a set of KPIs to reduce the risk while we maximize the time to value. Let me explain with an example. So let's put the analogy of drug development process. Drug development typically on average takes around $2.5 billion per drug, and on average 5 to 10% of potential drugs will successfully pass all phases of drug development, all these 5 toll gates, and they are very structured, they're very well known. So since the execution of drug development project is exceptionally costly, the company doesn't have enough resources to deal with all the projects, right? So basically we need to make selections. There are factors to consider when doing this selection. The key factors are success risk, expected revenue, development cost, and budget allocation. Now, this is our decision science process. This is a very structured process to develop models, and I strongly recommend, if you don't have it, you build your own. You can use actually a very good paper I will include in my notes, which is basically, it was published last year, June last year, in Nature, Standards for Evidence in Policy Decision Making. And it's a super simple way to actually weight your evidence while you are progressing in this journey. But let me explain the concept. When you start defining a decision science challenge, you start with a theoretical value. You start trying to guess what are the odds of adding value to a previous decision-making baseline. So it's theoretical. You start with a theoretical value. Maybe you use some data to create your theoretical business case, right? But it's high risk at this moment. High risk in terms of adding value at the end. So at the end means that the user actually is taking decisions with this model. So what we do typically is we do a proof of value, right? We start iterating. Maybe you use CrisDM for doing proof of values, or you use another method. What we end at this proof of value is with an empirical value. And this is a backtesting value. It means that you have simulated your decision making with the model versus your previous historical baseline. So you are closer to the facts at this stage. And you may think to start doing clinical trials, start doing small trials to test the model in production, to see how humans behave or how the new process works in the final stage. Well, if you replicate your experiments and you end up with the same results, positive results, basically you are really close to the final stage, right? And you would like to have continuous value eventually measured, meaning to capture how the humans we are taking now, the new decisions improved by our algorithms. So this journey, coming back to the analogy, this journey is very similar to this drug development journey, 5-step process that we talked before. Now, there are two key uncertainties in this process. Two key uncertainties meaning value, and we talk about this probability to win times expected value, the proof of value phase, but we also have the probability to win after the proof of value, the empirical value. And then finally, you will have to measure continuously how your model is being used in some kind of a continuous process. So that's the final stage of continuous value. Well, that's the value part, but you have a time cost part, which is basically also uncertain. You start with an estimation around how long you're going to be iterating within your proof of values, and also you will have the final actuals of these iterations, right? So it's key to start forecasting. It's key to start measuring the accuracy of this forecast, and also very important to start saving all these forecasts and iterations so you can use this data eventually. And eventually you would like, of course, to maximize this function, right? So let's talk about the portfolio productivity. This is the final function that you may want to optimize. And there are different elements in the numerator of this function. There is this work in progress or work in process, which basically mentions the number of projects that we are actually running at the moment. Of course, each project should be a score or weighted time the probability to win. This is evolving along your iterating in your fact-based journey. You will get a more probable time to win or probable win. And then you have the value profit. You have the additional value that you have accomplished. And this is again starting with the theoretical value, then empirical value, and then finally the continuous value. So this is the numerator, and then you have the denominator of this function, which is the time to win, which is the cycle time for all this journey from proof of value and deployment, times your cost. While this function, it's clear that you could optimize or you could maximize the function by increasing the probability to win, or you could eventually reduce the time to win in order to maximize this function. There are different approaches basically to optimize this function. But it's also important that we reflect that these elements that comprise this equation are linked. So it means that changing one element can often negatively or positively affect the other. For example, if you have sufficient pipeline in the work in progress, it is crucial, of course, to basically for basically increasing the attrition rates, to increase basically the probability of having empirical value. But if you have a lot of WIP, the issue is that you could end up with a lot of cost, and that could be also increasing your cycle time and eventually reduce your productivity. So for dealing with all these constraints or all these correlations, what you can do is use what is called chance constraint programming. And this is actually a pretty well-known technique that can handle uncertainty. And this uncertainty that we have mentioned is the key to optimize the sequence and define what should be in your pipeline, in which order. So for a wider audience, chance constraint method is one of the major approaches to solve any optimization problem under uncertainties. And it is a formulation of optimization problem that ensures that probability of meeting a certain constraint is above a certain level. And in other words, it restricts the feasible region, so the confidence level of a solution can be high. So let's talk about the benefits of diversification. This is an important aspect of your portfolio. Typically, you could have equally weighted portfolios, or you could have weighted portfolios. In financial markets, if you put the analogy of financial markets, if you invest in one stock, you know, it's quite risk correlated, right? And typically you could be exposed by, you know, fluctuations of the market, by, you know, fluctuations of the industry, you know, project or industry performance, etc. So you would like to combine different stocks, right? That's by definition the approach for portfolio management in financial markets. So we need to diversify, basically. An example of this diversification in financial market is the market cap weighted portfolio. And typically this creates individual weights based on the size of the companies, measured by market capitalization, etc. Well, the risk here, if you think about this analogy, the risk in data science is that there's a lot of unknown unknowns here. We don't know exactly what is the, you know, asset historical value at risk. And basically we need to start with simple KPIs. And some simple KPIs is to start measuring the number of your projects. What is the number of projects along the time? But also very easily you could start guessing what is the correlation between these projects. How? You could start thinking about how how these projects are combined. If they are basically under the same decision-making organization, for example, or the same customers, or the same markets, or they connect with the same type of channels, for example. But it's important that you start thinking about how this correlation is connected in your portfolio. Now let's talk about 5 examples, 5 of projects that we would like to run in this portfolio. Now imagine that you could know upfront what is the probability of winning and what is the value and what is the time that we are going to take. That could be perfect, of course. Then you will have the perfect sequence. And by definition, this is not going to happen, of course. So you could say that, the worst case is that we do some kind of random prioritization. It could end like this. But you need to start incorporating at the beginning of this process the maximum amount of good forecast. How to do that? Basically, you need to start with the right teams. You need to start with the right people. Business people that understand the current performance of decision making and also understand the hypothesis. But also you need to start with the right data engineers, so people that can basically forecast the probability of succeeding because they understand the current quality of data. So if you will say that you build your perfect team at the beginning with the right data, basically you are closer to this best optimization prioritization. Now let's talk about the next step. Let's think that we have iterated now for a while, and now we have actually historical baselines of our human-based prioritization. And this is, for example, what we have in this green curve here. We have an understanding of our probabilities of success and what is our hit rate, basically. So we can understand the probability that we did historically, and also the time that we were expecting to close this opportunity. But also we can reflect about the accuracy of these 2 elements. So imagine that you could build a model, and that's exactly what we have done. We built a model, a machine learning algorithm, that can explain the probability of success and the time to win based on the different iterations and the parameters of these iterations, like the domain that we have started working, the type of market, the type of business, etc., etc. What we have seen is that by doing this model and backtesting this model compared to our previous prioritization, we could increase significantly the productivity. And this productivity at the end is what we would like to maximize. Again, this is a backtesting result. So we are one step farther to the facts, but we need to now test it in a clinical trial. And this is again a recommendation system. So it's a system that will be helping us to prioritize using also our input. But our final decision, of course, will need to be made by us, not by the model. Now, let me summarize a little bit of the key takeaways of this speech. And the first one is, of course, to define your process, define your data science process, and of course, define your productivity function. What are you trying to maximize? That is the key to start with. Second element is that you would like to measure the correlation of your portfolio to understand the risk exposure of your portfolio. Third element is that, of course, the proof of value by definition has higher risk than any deployment. You need to make sure that these proof of value iterations are efficient. So you are trying to add value in small steps rather to build the perfect model. The fourth point is that you would like to increase your investments when the empirical value is known. And furthermore, if you have clinical trials applicable and replicable. Then you would like to reduce your deployment cycle time. How to do that? Typically, you have good collaborations with your DevOps teams. You have a good and standard method for the model deployment, pipeline management, etc. This is good, and this is very key at this stage. The last but not least, build a model to reduce this human bias. If you have a human performance of the probability to win and the time to win and the understanding of this accuracy, why not to start basically building your own model for predicting these probabilities and this time. And finally, the final step, try to use this chance constraint programming to decide your portfolio sequence in order to maximize the value. So I hope you have enjoyed the session, and remember, this is about protecting what is good. See you around. Bye.